Good morning, students. In this session, I'm going to discuss gravitation. Okay, we'll wait to 2 minutes to join the rest of the students. Okay, I'll start. Let them join. Gravity and gravitation. Gravity is nothing but acceleration due to gravity. Gravitation means universal gravitational. So, gravity is nothing but acceleration due to gravity. This acceleration due to gravity is the force of attraction between a body and a planet. Force of attraction. So force of attraction between a body and a planet. Is the force of attraction between a body and a planet is called as the gravity. Gravitation. Capital G. It is the force of attraction between any two bodies in the universe. The force of attraction between any two bodies in the universe. Is called as the gravitation. Acceleration due to gravity, small g, that is not constant, that changes from planet to planet, place to place. Generally, we will take that acceleration due to gravity on the surface of Earth is 9.8 meters per second square, or for our simplification, we will take it as 10 meters per second square also. G, we may take 9.8 meters per second square or 10 meters per second square. There is no restriction. We have to use only G 9.8 meters per second square only. There is no restriction. A small variation will be there. It's not a problem. Then according to our convenience, both of them we are using. What is universal gravitational constant value? This universal gravitational constant value is 6.67 into 10 power minus 11 Newton meter square per kg square. 6.67 into 10 power minus 11 Newton meter square per kg square. This is the value of the universal gravitational constant. This is constant everywhere. It is not affected by any pressure, temperature, or local conditions. It is everywhere in the entire universe, same value it will be there. That's why they have called it as universal gravitational constant. When we come to this, to explain the planetary motion, Kepler, he gave 3 laws called as Kepler's laws of planetary motion. Kepler's laws of planetary motion. Kepler's laws of planetary motion it is. What are the Kepler's laws? First law. First law, it states whenever we take this is the elliptical path, every planet that revolves in an elliptical orbit, and sun will be at one of the foci. For the elliptical path, only one center won't be there, 2 centers will decide. This is called F1, called as a foci. This is called as foci, means a center like. This is called as the foci. This is called one more foci. Every planet that revolves around the sun, and sun will be at any one of the foci. So this is that planet, and sun may be at the center, or sun may be at this center, or sun may be here. So I am taking sun is here. Every planet that revolves around the sun, and sun will be at any one of the foci. Every planet revolves around the sun, and the sun will be at any one of the foci. This is called as the Kepler's first law of planetary motion. Next. Second law. When we take elliptical path, let us suppose this is the elliptical path. In this elliptical path, the radius vector drawn from the planet to the sun. Let us suppose this is that big one is called as a semi-major axis. Small one is called as the semi-minor axis. So sun will be at this center, and let us suppose it is a planet. A radius vector drawn from the planet to the sun. Radius vector drawn from the planet to the sun sweeps out equal areas in the equal intervals of time. Let us suppose this is the area covered by it. This is the area covered by it in the time period delta t. Delta A is the area covered by it in the time period delta t. In delta t time period, if it covers delta A area, and again, if I take this same time period whenever it is considered, this is another position. Now, delta A is the same area it will cover if time period will be same. Let us suppose this is a planet. Planet moves from the point A to B in time interval delta t. Then it covers delta A is the area covered by it. If it moves from the point C to D, the area covered by it is delta t if the time period is delta A, if the time period is delta t. So same time period whenever we consider, delta is the time period. Same time period whenever we consider, area covered from A to B will be same as the area covered from C to D. Area covered from A to B will be equal to area covered by the body from C to D. This is the second law of motion. According to Newton's second law of motion, the area covered, rate of area covered, dA by dt is equal to L divided by 2m, where L is called as the angular momentum. When the body moves in circular path, the momentum of the body is called as the angular momentum. See here, when the planet is far from the sun, it moves slow. When the planet is far from the sun, velocity will be minimum. When the planet that approaches the sun, velocity of the planet will be maximum. It increases. So when the planet is far from the sun, velocity is less. Means velocity is less means what? Distance will be more. Distance is taken as a maximum distance, minimum velocity. So minimum distance, so maximum velocity. Minimum distance, maximum velocity will be there. So we'll write that when the planet is revolving around the sun, a radius vector drawn from the planet to the sun sweeps out equal areas in the equal intervals of time. This is that time interval is same, delta t. So area covered from A to B will be equal to area covered from C to D. This is from second law, from the Kepler's second law. Otherwise, dA by dt is equal to L by 2m is one formula for each. Then V maximum into R minimum. V maximum into R minimum is equal to V minimum into R maximum. This is also formula we have to write. As I have taken, when the planet is far from the sun, it moves slow. When the planet is near to the sun, it moves fast. So they may ask that these are the different positions. A planet is at the point A. A planet is at the point A. I'll take here at the point A, at the B, and at C, and D, where the velocity of the planet will be maximum. They'll ask it. So maximum velocity we will get the at point D. We'll get the maximum velocity at the point D. This is called as maximum velocity. Where is the minimum velocity? At the point A. Minimum velocity will be at the point A we will get. Right. Next, Kepler's third law of planetary motion. Third law of planetary motion. It states that square of the time period of the planet is directly proportional to cube of the mean distance. Square of the time period of the planet is directly proportional to cube of the mean distance. This is Kepler's third law of planetary motion. T is a time period. R is called as a mean distance. So then T square is equal to 4 pi square divided by gm into R cube. Like this also we may write. So T square is equal to 4 pi square divided by gm into R cube. This is for the time period. Right. So whenever we come to that universal law of gravitation, according to universal law of gravitation, universal law of gravitation. Universal law of gravitation. According to universal law of gravitation, the force of attraction between any two planets is directly proportional to product of their masses and is inversely proportional to square of the distance between them. Let us suppose two bodies, they are separated by a distance. Up to their centers we have to take. The masses of the two bodies are m1 and m2. m1, m2 are the masses of the two bodies. Then the separation between them is taken as r. Then the force of attraction that depends on masses F is proportional to m1 and m2, and F is inversely proportional to square of the distance between them. Inversely proportional to square of the distance between them. Combinedly, we'll write that F is proportional to m1, m2 divided by r square. Or we'll take that F is equal to replace this proportionality, we multiply with a constant where G is called as the universal gravitational constant. So F is equal to G m1 m2 divided by r square. F is equal to G m1 m2 divided by r square. This is the universal law of gravitation. This is the universal law of gravitation, where G is called as universal gravitational constant. G is called as universal gravitational constant. Let us suppose a body is taken. Let us suppose it's a planet. On the planet, a body of mass m is there. On the planet, a body of mass m is there. Radius of the planet is taken as a small r. Small r is the radius of the planet. Then weight is nothing but force. Weight is nothing but force. Then instead of this, in the equation number 1, we may write F is equal to mg. From equation number 1, we will write. Actually, we have to take the distance up to the center of this body. But radius of the Earth is 6,400 kilometers. When compared with the radius of the Earth, this radius of the body is negligible. That's why radius of the body no need to take. Then in the place of F is equal to what? F is equal to G m1 m2 divided by m1 m2 divided by r square. F is equal to G m1 m2 divided by r square. So F is equal to mg. Mg is equal to G m1 m2 divided by r square. Both sides we will cancel. M1 I am taking as this one. Its mass is taken as m1 is equal to m, and I'll take that m2 is equal to, this is taken as m2 is equal to capital M, mass of the planet it is. Therefore, we will write here gm into m, g into capital M into small m, we may write. Both sides the small m gets cancelled. What is there? Acceleration due to gravity, g is equal to gm divided by r square. Acceleration due to gravity, g is equal to gm divided by r square. This is capital G. This capital G, instead of this r square, what we have to write? Capital R we have to write. Capital R square we write. Therefore, acceleration due to gravity, g is equal to gm divided by r square. Therefore, acceleration due to gravity that depends upon mass of the planet, and acceleration due to gravity that depends upon the radius of the planet. So when two different distances are taken in terms of the mass, radius of the acceleration due to gravity is inversely proportional to square of the distance. When we take g1 divided by g2 is equal to r2 divided by r1 whole square. This will take that g1 by g2 is equal to r2 by r1 whole square. This is according to this relation between capital G and small g. In terms of the mass, g is proportional to inversely proportional to r square. You have to remember this. In terms of the mass only, g is inversely proportional to r square. g1 by g2 is equal to r2 by r1 whole square. If radius of the planet that increases, its acceleration due to gravity that decreases. If mass of the planet is more, acceleration due to gravity on the planet will be more. Like that, we will take. Or in terms of the mass, it is in terms of the mass, g is equal to gm divided by r square we have taken. That same we may take in terms of in terms of mass, G is equal to Gm divided by R square. This is okay. Next, in terms of density, then we take that density is equal to density. I used to write capital D. Density D is equal to mass divided by volume. Density is D is equal to mass by volume. Then mass is equal to volume into density. Mass is equal volume into density. Therefore, M is equal to volume will be equal to 4/3 pi r cube into D. In the place of mass, we'll write it. G is equal to G into, in the place of mass, we have to write 4/3 pi r cube into D. It will be 4/3 pi r cube, 4/3 pi r cube into D whole divided by R square. Combinedly, one R square gets cancelled. There we will write small g is equal to 4/3 pi r cube pi r into g d. 4/3 pi r gd. So R square it gets cancelled. Then G is equal to 4/3 pi r into gd. This is the formula to calculate acceleration due to gravity. Or acceleration due to gravity that depends upon radius of the planet. It depends upon that. In terms of the density, acceleration due to gravity is directly proportional to radius. For example, whenever the body we are taking into depth of the earth, gradually acceleration due to gravity that decreases. On the surface of earth, acceleration due to gravity will be 9.8 meters per second square. If we are going away from the surface of the earth or into the depth of the earth, acceleration due to gravity that decreases. When we are going away from the surface of earth or if we are going into depth of the earth, in such case, acceleration due to gravity G that decreases. It will be maximum on the surface of the earth only. On the surface of the earth, it is maximum. At the center, it will be zero. Right? Whenever we are taking the body, at that body is here, acceleration due to gravity is zero. So as the body is coming from the center to the surface of the earth, G is proportional to R. Acceleration due to gravity that increases. Acceleration due to gravity that increases. Where? From the center of the earth to the surface of the earth. Here maximum value will get it. While we are taking this body from the surface of earth to the higher altitudes, acceleration due to gravity again that starts decreasing. Okay, then we may plot the graph for the variation of the G with the depth and height. Let us suppose this is the graph. On this graph, acceleration due to gravity we are taking along the y-axis and distance we are taking along the x-axis. Acceleration due to gravity is like this and the distance r is like this. Then we have to take that the relation between these two, that acceleration due to gravity that increases, acceleration due to gravity that increases up to here and afterwards it starts decreasing. Then acceleration due to gravity that is directly proportional to r up to here, and from here acceleration due to gravity is inversely proportional to r square. So it is that center of the earth. This is the center of the earth. At this point we will take earth, surface of the earth it is. At this point small r is equal to capital R. Means what? This is at this point small r and capital R will be same for this point. When the surface of the earth is considered, at the surface of the earth, small r and capital R will be same. Right? So acceleration due to gravity that is maximum on the surface of the earth. G is equal to what? Gm divided by R square. This is the maximum on the surface of Earth. It depends upon some factors. So variation of G with height. Change in acceleration due to gravity due to that height whenever we take. On the surface of the Earth, it is maximum. G is taken, whose radius is taken as capital R. When we take the body to a higher altitude, if you take it to that higher altitude, then this high at this point acceleration due to gravity gh. So we have taken to a height h. At this height acceleration due to gravity is gh. Then gh is equal to g into 1 minus 2h divided by r. 1 minus 2h divided by r we may write. Otherwise, gh divided by g is equal to gh divided by g is equal to r by r plus h whole square. Any of these formulas we may use. Gh by g is equal to r by r plus h whole square. So acceleration due to gravity at a height h is gh. Gh is equal to g into 1 minus 2h divided by r. 1 minus 2h divided by r. Then whenever we take this acceleration due to gravity that changes with the height, the change in acceleration due to gravity delta g divided by g is equal to 2h divided by r. Delta g by g is equal to 2h divided by r. This is a formula to calculate otherwise the change in acceleration due to gravity. Otherwise we may take one more formula. We may take that one more formula. These two formulas are there. See, this is gh is equal to g into 1 minus 2h divided by r. Gh by g is equal to r by r plus h. Which formula we have to use? If h is much less than that of the radius of the Earth, we have to use this formula. If h is much less than that of the radius of the Earth, we have to take this formula. Gh by g is equal to r by r plus h whole square. Then delta g by g is equal to 2h divided by r. Delta g by g is equal to 2h divided by r. This is the formula to calculate change in acceleration due to gravity due to that height. R, weight, if you take that delta w divided by w is equal to 2h divided by r. Delta w by w is equal to 2h divided by r. So Redmi 9, please mute. This who is Redmi 9, please mute. Okay, thank you. This w delta w divided by w is equal to h divided by r. This is the variation of g with the height. Then variation of g with the depth. Variation of g with the depth. When we take that body, it is there on the surface of Earth, acceleration due to gravity is maximum. When it is at the surface of Earth, acceleration due to gravity is maximum. While we are going to that depth, the acceleration due to gravity that decreases. The decrease in acceleration due to gravity that we have to calculate. So for that, we take in terms of density. What is the formula for this in terms of the density? G is equal to 4 by third pi r into gd. Then acceleration due to gravity when the body is there on the surface of Earth, G is equal to 4 by third pi r into gd. Then acceleration due to gravity of the body at a depth d. at a depth d. Let us suppose from the center at a depth d, I want acceleration due to gravity. This will be capital R minus small d. This will be equal to capital R minus small d. Therefore, at the depth d, the acceleration due to gravity, GD is equal to 4 by third pi into R minus d. R minus d into GD. This is the formula. So first equation and second equation. I'm writing equation number 2 and equation number 1. Acceleration due to gravity at a depth d is equal to g into 1 minus d divided by r. This is the formula to calculate acceleration due to gravity at a depth d. This is a formula to calculate acceleration due to gravity at a depth d. Then, if you want to calculate this acceleration due to gravity due to that depth d, delta g divided by g is equal to delta g by g is equal to d divided by r. D divided by r we will take. R, we may take this delta w divided by w is equal to d divided by r. D divided by r. Like this we will write. And one more formula is there. What is this? Let us suppose g is equal to gm divided by r square. They'll say that if radius of the planet is increase 2%, what is the increase in acceleration due to gravity? They'll ask it. Radius of the earth is 2%. What is the acceleration due to gravity? So g is inversely proportional to r square. This will write delta g divided by g into 100 is equal to, this square is there, that square will write as coefficient 2 into delta r divided by r into 100. See, delta percentage of change in radius is given. Percentage of change in radius is given as 2% is nothing but delta r divided by r into 100. Delta r by r into 100 is equal to 2%. It is given delta r by r into 100. Delta r by r into 100 is equal to 2%. So therefore, delta g divided by g into 100 is equal to 2 into. In the place of delta r by r into 100, we will take 2%. We will take 2%. Therefore, delta g by g into 100 is equal to 2 2s are 4%. It is. Delta g by g into 100 is equal to 4%. Like this, we will take. This is one method, right? This acceleration due to gravity that depends upon the shape of the earth also. Acceleration due to gravity depends upon the shape of the earth also. Let us suppose this is the earth. Earth is not the exact sphere. It is flattened at the poles and bulged at the equator. It is at the poles. At the poles, it is flattened, and at the equator, it is bulged. At the poles, acceleration due to gravity is 9.83 meters per second square. Acceleration due to gravity at the equator is 9.78 meters per second square. As acceleration due to gravity is less at the equator, it will give little bit more quantity of mass here, which is profitable to purchase the sugar at the equator or at the poles, they'll ask. Which is profitable to buy the sugar either at the equator or at the poles, they'll say that. So then we'll say that it is better, or it will get a little bit more quantity of the sugar at the equator, because acceleration due to gravity at the equator is less. That's why a little bit more quantity of the sugar we will get at the equator. So we'll say that it is better to buy at the equator, that will say. Right? These are the expressions for the variation in acceleration due to gravity to with the depth and with the height, right? And local conditions also will be there. Rotational speed of the earth is also there. Let us suppose rotational speed of the earth is increased to 17 times of the present situation. Present it is revolving about 1000 means 1500 kilometers per hour speed. It is revolving. Earth is rotating. The rotational speed of the earth is about 1500 kilometers per hour. Even though it is revolving in that speed, we are not experiencing that, because we are there, and that we are a part of it. We are also revolving, we are also moving along with that earth. That's why we don't feel that velocity experience. So rotational speed of the earth is about 1500 kilometers per hour will be there. Okay, if the rotational speed of the earth is increased to 17 times, rotational speed of the earth is increased to 17 times the present speed, then the people who are there at the equator, they fly off. Acceleration due to gravity at the equator will be 0. If the rotational speed of the earth is increased to the 17 times of the present situation, then acceleration due to gravity at the equator will be 0, and the people who are there at the equator, they'll fly off. Right? Gravitational potential. Gravitational potential. Gravitational potential. Gravitational potential. This gravitational potential V at a point, when I take V is called as a gravitational potential. So V is equal to Gm divided by V is equal to Gm divided by R. Gravitational potential V is equal to Gm divided by R. That means to move a body from one point to other point, how much work is needed? That is called as the gravitational potential. Our gravitational potential energy is there. Gravitational potential energy. It is nothing but amount of the work done. It is nothing but work done needed to move a body from the infinite distance to at a distance d from that point to bring it to a distance d. Means from infinite distance to the surface of the earth. To bring a body from infinite distance to the surface of earth, how much work is needed? Once again, I'll say that gravitational potential energy is the amount of the work done in bringing a unit mass from the infinite distance to a point in the field. In the field means this is the earth. Around the earth, the gravitational field will be there. We have to bring the body from infinite distance to a point P. Point P is in the under the influence of the gravitational attraction. So we have to bring the body from infinite to a point P. So how much work is needed for it? We say gravitational potential energy. So gravitational potential energy is equal to minus G m1 m2 divided by minus G m1 m2 divided by r square. Gravitational potential energy is equal to minus G m1 m2 divided by sorry r square won't be there, r only. Gravitational potential energy is equal to minus G m1 m2 divided by r. Sir, earlier you have written r square. What about that r? In the derivation, that r square we will take it. I mean, sir, r square will be minimized, or r square will become as r. It is there in the derivation. If you do the derivation, then only you are able to understand why we have taken r instead of the r square. Right? This is the gravitational potential energy. So this is a work done in lifting a body from the ground to a height h. Let us suppose if you want to lift the body from the ground to a height h. So the work done is also called as the gravitational potential energy. So to lift a body from the surface to a height h, gravitational potential energy will take that. So gravitational potential energy G is equal to minus G capital F. Gravitational potential energy. Gravitational potential energy, it is taken as minus G M1 M2 divided by R. So it is the work done in lifting to a height h. Whenever you want to lift, that work done is needed. So the work done in lifting to a height h will take that. Then work done in lifting to a height h, that will be equal to mgh into 1 plus h divided by r. H is that height through which we are lifting. If h is much less than that of the radius, means what? H is negligible. If h is very less when compared with the radius of that, then h by r we can minimize, means we can eliminate. So W is equal to mgh divided by 1, nothing but W. This W is nothing but gravitational potential energy. W is equal to mgh. This is the work done in lifting it through a height h above the ground, right? Then whenever we take that body, if you are throwing from the ground, if the velocity is velocity v is equal to 7.92 meters per second, velocity of the projection is less than this, the body will fall on the earth again. If the velocity of the projection is 7.92 less than 7.92 meters per second, then it will come back. The body will fall on the earth. Instead of that, when the body is when the body is projected with a velocity, it is 7.92 meters per second to 11 meters per second, not 7.92 kilometers per second. 7.92 kilometers per second to 11 kilometers per second. If the velocity of the projection is 7.92 kilometers per second to 11 kilometers per second. 11 kilometers per second. If velocity of the projection is 7.92 kilometers per second to 11 kilometers per second, in such case it will escape, it will be inserted into the orbit of the earth. When the velocity of the projection from the surface of earth is 7.92 kilometers per second to 11 kilometers per second, the velocity is called as the orbital velocity. So orbital velocity VO is equal to square root of GM divided by R. Square root of GM divided by R. R will take that. Small g is equal to GM divided by R square. Small g is equal to GM divided by R square. In the place of GM, we write GR square. We'll write GR square. Then VO is equal to square root of GR square divided by R. GR square divided by R. Therefore, VO is equal to square root of GR. VO is equal to square root of GR. This is the expression for the orbital velocity. So this is the velocity of the projection should be how much? 7.92 kilometers per second to 11 kilometers per second. If the velocity of the projection is greater than 11 kilometers per second, its velocity of the projection is 11.2 kilometers per second. If the velocity is 11.2 kilometers per second, If it is there, then the velocity is called as the escape velocity. The velocity is called as the escape velocity. If the velocity of the projection is 11.2 kilometers per second, then VE, E for escape, VE is equal to square root of 2gm divided by R. So VE is equal to square root of 2gm. Instead of gm, we'll write gr square. So 2gr square divided by 2gr square divided by R. Then one R gets cancelled. That is equal to VE is equal to square root of 2gr, square root of 2gr, or VE is equal to square root of 2 into VO. This is a relation between the escape velocity and the orbital velocity. VE is equal to square root of 2 into VO. Then whenever we take that escape velocity on the surface of Earth is minimum 11.2 kilometers per second. And for the moon, the escape velocity is 2.38 kilometers per second. Escape velocity on the sun, if you take, it is 42 kilometers per second. Escape velocity on the sun is 42 kilometers per second. This escape velocity is independent on angle of the projection. Escape velocity is independent on the angle of the projection. It depends upon the mass and the radius of the planet. It is independent on mass of the, it depends upon the mass of the planet and radius of the planet, and it is independent on velocity, means it is independent on angle of the projection. Okay, as means satellites, whenever we take satellites, they'll have the kinetic energy, potential energy, and total energy. So energy of the satellites, when we take kinetic energy of the satellite, Ke is equal to kinetic energy of satellite, Ke is equal to G capital M small m divided by 2 into R plus H. This is the kinetic energy of the satellite. Then potential energy of the satellite, I want. Potential energy of the satellites, PE is equal to minus G capital M small m divided by R plus H. PE is equal to minus G mm divided by R plus H. Then total energy, when we take total energy, TE is equal to minus G capital M small m divided by 2 into R plus H. This is the total energy. Ratio of the kinetic energy, potential energy, and total energies, whenever we take Ke is to Pe is to Te, if you write, it will be equal to 1 is to minus 2 is to minus 1. These are the ratio of the kinetic energy, potential energy, and total energies. These are the ratio of kinetic energy, potential energy, and total energies. Right? See, a mass we have to split. A mass we have to split into, a mass capital M is there, that we have to split into two smaller masses. We have to split into two smaller masses, M1 and M2. M1 and M2. Then to get the maximum force between them, we have to split this. M1 is equal to M by 2. M1 is equal to M by 2. M1 is equal to M by 2. And M2 is equal to capital M divided by 2. M1 is equal to M by 2 and M2 is M by 2. This is a maximum force. So for minimum force, to get the minimum force, that means we have split this mass capital M into two small masses, M1 and M2. In between them, we have to get maximum force or we have to get minimum force. That depends upon the masses. That depends upon the masses. We may get maximum force or minimum force. For minimum force between the two parts, to get the minimum force between the two parts, M1, if you take 1 kc, M2 will be capital M minus 1 kc. It should be M1 is 1 kg, M2 should be capital M minus 1 kg that we have to take. Okay, we will see the numericals part. Today the class is up to 8 o'clock only. This week I will take only up to 8 o'clock, right? See, this is a problem. A mass capital M is divided into two parts. A mass capital M is divided into two parts, xm and 1 minus xm for a given separation. The value of x for which gravitational attraction between the two pieces becomes maximum. I told you that a mass capital M is a mass capital M, we have to split it. We have to split this mass capital M into two parts. One part mass is taken as M1, other part mass is taken as M2. Then M1 is equal to M by 2. This is the mass is taken as M. This M2 is equal to M divided by 2. M1 is equal to M by 2 and M2 is also equal to M by 2. M by 2 and M by 2 we will take that. Next. Two spheres of mass, small m and capital M, are situated in air and the gravitational force between them is F. The space around the masses is now filled with a liquid of specific gravity 3. The gravitational force will be. So try to understand the problem. What is given? Two spheres are there. Two spheres of mass, small m and capital M, are there. In between them, initially force is taken as F. F is the force between them initially. F is the force between them initially. Then, if the space is filled with, specific gravity, this is filled with the specific gravity, then the new force, how much it will be there? They are asking. There is no change. So gravitational force is independent on the factors like what will take that pressure, temperature, or the medium between the two masses. So whatever it may be the medium between the two masses, gravitational force won't be affected. That's why when the space between the two bodies is filled with a dielectric medium, then also force will be same. F dash also will be equal to F. F dash also will be equal to F. Therefore, force is taken as F. Then the gravitational force will be taken as F. Next problem. See, explanation it is given. Gravitational force does not depend upon the medium. Right? Next. This I'll prove. If the change in value of acceleration due to gravity at height h above the surface of Earth is same at a depth below it, then the relation between these two we have to take that. Acceleration due to gravity at a depth, how much it is there, that is acceleration due to gravity at a height, that will be same. That will be same. What did they give? Acceleration due to gravity at a height h is gh is equal to g into 1 minus 2h divided by r. 1 minus 2h divided by r. Then acceleration due to gravity at a depth gd is equal to g into 1 minus d divided by r. But it is mentioned distance is taken as x. So in this we'll write GD is equal to G into 1 minus x divided by R. From this we will write G GH is equal to GD, we write. It give according to given condition, GH is equal to GD. From this we will write G into 1 minus 2H divided by R is equal to G into 1 minus D divided by R. 1 minus D divided by R. So G and G gets cancelled. Then what is there? Instead of D, we have tried as X here. We have tried this one is X. Right. From this 1 minus 2H divided by R is equal to 1 minus X divided by R. 1 minus X divided by R. So there we will take this 1 gets cancelled, minus get cancelled. So 2H divided by R is equal to X divided by R. Both sides will get cancelled. R. Therefore, X is equal to R. X is equal to 2H. This is the correct answer. Okay. So next problem. Time period of simple pendulum on a freely falling artificial satellite. Time period of the simple pendulum in a freely moving artificial satellite. So in that, acceleration due to gravity, that will be taken as 0. So then time period that will become infinite. Time period will be infinite. Okay, I'm going to stop the class here. Then we'll see the remaining problems in the tomorrow's class. Thank you.
Thank you, sir.
Yes.